Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's get started on our set of questions for today's session. Okay, so question 1 says to determine the molar mass of urea to 4 significant figures using the values in the periodic table. Okay, so urea. Let's first draw out its structure. It has 2 amine groups on a carbon and also a double bonded oxygen in the middle. So it kind of looks like this. So its chemical formula is CH4N2O. So now that we know the chemical formula of urea, we can calculate its molar mass. So when calculating molar mass, we need to take into account all the different atomic masses of the atoms involved in urea, and also how many of each atom there are in the molecule as well. So the molar mass of urea will be equal to the molar mass of carbon plus 4 times the molar mass of hydrogen plus 2 times the molar mass of nitrogen plus the molar mass of oxygen. Okay, so these values can be found on your periodic table. Carbon's molar mass is 12.01 grams per mole, and hydrogen's molar mass is 1.01 grams per mole. Nitrogen's molar mass is 14.01 grams per mole, and oxygen's is around 15.99 grams per mole. Okay, so now that we have our formula, we can just add these values up and we get a total molar mass of 60.06 grams per mole. Okay, so now let's look at what the junior tutor said. Molar mass is defined as the amount, usually expressed as mass in grams, of 1 mole of a substance. It can be calculated by obtaining the sum of the products of the number of moles of each element and 1 mole of the compound, as shown in the chemical formula. The corresponding molar mass of the element. The number of atoms in 1 mole of a substance is constant. So this is Avogadro's constant, which is 6.022 times 10 to the 23 atoms per mole. So the molar mass of an element in grams per mole has the same value as the atomic mass of the element in atomic mass units, or AMU. Urea is an organic compound classified as an amide. It has 2 amino groups linked by a carbonyl group. Chemical formula is CONH2. In 1 mole of urea, there are 1 mole of carbon, 1 mole oxygen, 2 moles of nitrogen, and 4 moles of hydrogen. Okay, so they also got 60.0606. So this solution is correct. Okay, question number 2. What is the oxidation number of chromium in Cr2O7 ion? Okay, so first let's define what an oxidation number is. Okay, so the oxidation number is the total number of electrons that an atom has lost or gained to form a chemical bond. Okay, so there are certain rules to when calculating the oxidation number. But for our case, one of the rules is that for oxygen, oxygen typically has an oxidation number of -2, except when it is a peroxide. Okay, so that will be helpful for us when finding the oxidation number of chromium. And another helpful tip is that the sum of the oxidation numbers in a compound is equal to its overall charge. So let's say we had a compound that was neutral. If it had something that had an atom that had an oxidation number +1, then the other atom that it is bonded to would have an oxidation number of -1. So we know that when you add those charges together and get a neutral molecule, their oxidation number, the sums, will be equal to 0. Okay, so these two rules are helpful in answering this question. So we know that the sum of the oxidation numbers in a compound is equal to its overall charge. So if we had the overall charge this is equal to 2 times the oxidation number of chromium plus 7 times the oxidation number of oxygen. Okay, so now let's sub in what we know. We know the overall charge of this ion is -2. And we're trying to solve for the oxidation number of chromium. And we know the oxidation number of oxygen is -2. So 2 plus 14 is equal to 2 times the oxidation number of chromium. So 12 over 2. Making the oxidation number of chromium equal to 6, or positive 6. Okay, so let's see what the junior tutor said. The oxidation state of an element refers to the total number of electrons that the element lost or gained to form a chemical bond, other atoms resulting in a chemical compound. Oxygen has the ability to gain 2 electrons, resulting in an oxidation state of -2. However, there are exceptions, including molecules or polyatomic ions that contain oxygen-oxygen bonds. Oxidation state of chromium varies to +2, +3, and +6, depending on the atoms it will attach to. To determine the oxidation state of chromium in the overall compound, we must consider that the compound is charged, thus the overall charge must be -2. Calculating the oxidation state of chromium, they have the same equation and also got +6. So this solution is correct. Okay, so question number 3. What is the molar mass of the sulfate ion SO4 2-? Okay, so when calculating the molar mass, we do not need to take into account the charge of the overall ion. The only thing that we're interested in is the molar mass of this sulfate ion. So to solve for the molar mass, we need to find both the molar masses of sulfur and oxygen. So it's going to be equal to the molar mass of sulfur, which you can just find on your periodic table, plus 4 times the molar mass of oxygen. So the molar mass of sulfur is equal to 32 grams per mole, and the molar mass of oxygen is around 16 grams per mole. So if we added these values up, we end up getting total molar mass of 96.06 grams per mole. Okay, so now let's see what the junior tutor said. Anhydrous sodium sulfate is the anhydrous sodium salt form of sulfuric acid. It dissociates in water to provide sodium ions and sulfate ions. It is also an electrolyte replenisher and is used in isosamic solutions so that administration does not disturb normal electrolyte balance and does not lead to absorption or excretion of water and ions. Okay, so they have some properties of sodium sulfate. And to solve for the molar mass of the sulfate ion, we will use the molar mass of the sodium sulfate given above and subtract 2 times the molar mass of sodium. So since the atomic mass of sodium is 22.99 grams per mole, we will have the following. So they have the total molar mass of sodium sulfate minus, I'm guessing, 2 times 22.99. And they also got 96.06. Okay, so this solution is correct. That's a different approach in solving this question. Okay, so question number 4. Question number 4. Oxalic acid, which is H2C2O4, 2H2O, which has a molar mass of 126.07, is often used as a primary standard for the standardization of an sodium hydroxide solution. If 0.147 grams of oxalic acid dihydrate is neutralized by 23.64 milliliters of sodium hydroxide solution, what is the molar concentration of the sodium hydroxide solution? Oxalic acid is a diprotic acid, and what is the balanced equation? Okay, so let's write out the equation. If we had oxalic acid plus sodium hydroxide reduces water and a salt, which would be sodium C2O4. Okay, so this is the neutralization reaction. And now we have to balance this equation. So we have 2 sodiums on our product side and only 1 sodium on our reactant. So we put a coefficient of 2 in front of sodium hydroxide. And now we have 4 hydrogens on our reactant side and only 2 on our product side. So we put another 2 in front of the water. Okay, so now everything should be balanced. So let's write down what was given. We have the molar mass of oxalic acid, which is equal to 126.07 grams per mole. And we also know the volume of sodium hydroxide that was used to neutralize. It was 23.64 milliliters. And we were also given the mass of oxalic acid, which was 0.147 grams. Okay, so the first step is to, let's see. Okay, so we're given the mass and the molar mass of oxalic acid. So the first step is to find the number of moles. So number of moles is mass over molar mass. And we have 0.147 grams and 126.07 grams per mole, giving us a number of moles equal to 1.17 times 10 to the negative 3 moles. Okay, so step 2 is to use mole ratios to find the number of moles of sodium hydroxide. So we know that we have 1.17 times 10 to the negative 3 moles of oxalic acid. And to find the number of moles of sodium hydroxide, we need to multiply by the molar ratios. So we can find this by looking at our balanced equation, and we can see that 2 moles of sodium hydroxide are needed to react with 1 mole of the oxalic acid. Okay, so we know we did it correctly if our oxalic acid moles cancel out, and we're left with moles of sodium hydroxide, which is equal to 2.34 times 10 to the negative 3. Okay, so now step 3 is to calculate the concentration of sodium hydroxide. Okay, so the formula for concentration is equal to the number of moles over the volume. So we know that we have 2.34 times 10 to the negative 3 moles of sodium hydroxide. And we also know the volume, which is 23.64 milliliters. But since the units for concentration are in moles per liter, we can convert this to milliliters by dividing by 1,000. So this is because there are 1,000 milliliters in 1 liter. Okay, so we get a final concentration equal to around 0.098 moles per liter. Okay, so now let's see what the junior tutor said. By definition, the law of conservation of energy states that mass is neither created nor destroyed. This is the basis for a balanced chemical reaction and equation, where the number of atoms present on either side of an equation is always going to be equal. The definition of molar mass is the mass of 1 mole of a compound, while molarity is the number of moles of a solute in a unit volume of solution. Here we have the equation for the molarity, which is equal to molar concentration, number of moles divided by volume. And here we have a balanced equation where the molar mass of oxalic acid is 126, molar mass of sodium is 40. And they said that the 126.07 grams is really needed for standardizing the 80 grams of sodium hydroxide. So they converted their units to mass instead of number of moles. And the given 0.147 grams of oxalic acid is used as a primary standard for standardizing sodium hydroxide. So they did a ratio where 0.147 divided by 126.07. So this is number of moles, or the mass of oxalic acid divided by its molar mass. And then they multiplied by 80 grams, which is the molar mass sodium hydroxide multiplied by 2 to get 0.933 grams. And then for molarity, they divided that by the molar mass of sodium hydroxide and then divided by the liters to also get 0.098. Okay, so the answer is correct. It may be easier to find the number of moles to calculate the number of moles of sodium hydroxide using molar ratios. then calculating concentration. Okay, so question number 5 is to draw the products of the complete hydrolysis of a ketal. Draw all the products of the reaction. Okay, so we start off with the ketal. And it reacts with water in acidic solution. So that means in the solution, we have H3O+, which is protonated water. So, or the hydronium ion. So what happens first is one of the lone pairs from our reactant will come in and deprotonate this hydronium ion, forming water, to get the following intermediate. So now we have a protonated oxygen that will have a positive charge, like so. And to relieve the positive charge, one of these oxygens will come down to form a double bond and kick off this whole group entirely. Making one of our products a 3-carbon long alcohol group. So this is one of our products, which is propanol. Okay, so after this propanol is formed, or propanol, we still have left over a double bonded oxygen that has a positive charge. And this kind of like side group here, like that. So from here, another water molecule can come in and attack the carbon beside the double bond, like so, and brings the pair of electrons up to neutralize that oxygen. So now, this is now a neutral oxygen, and we have a water group that has a positive charge, like so. And to relieve that positive charge, another water molecule can come in and deprotonate, take one of the hydrogens, to give us this intermediate. Where we have a newly formed alcohol group, like so. So now the lone pairs on this oxygen. So now it's a similar mechanism to how we started. This will come in and take one of the hydrogens and a hydronium ion. And have a positive charge now. And then similarly, the lone pairs from the alcohol group can come down and kick off this entire molecule entirely to get our second product. So I'm going to show it coming off up here, which is a 2-membered or a 2-carbon long alcohol, which is ethanol. And our other final group will now have a double bonded oxygen that is protonated, and this has a positive charge. And now water can come in to deprotonate it, bringing this down. And we're left with our final product, which is this ketone group. So this is 2-butanone or butanone. Okay, so this is the complete hydrolysis of this ketal. So you can see that it's like a long mechanism, but it kind of gets redundant in protonating and then deprotonating. But you can see our final products would be propanol, ethanol, and 2-butanone. Okay, so now let's see what the junior tutor said. When a ketal is treated with aqueous acid, a cleavage reaction results in a ketone and 2 alcohols. Scheme 1 shows the mechanism by which these products are formed in the case of the given reaction in the problem. Okay, so we have the protonation of one of the oxygens. Okay, this comes down to form propanol. Water will come in, get deprotonated, and then the same thing happens again. And we get ethanol and 2-butanone. So one of the carbonyl groups was protonated by the hydronium ion, making it more electrophilic. This is followed by the ejection of a leaving group, which is alcohol, and the formation of a double bond. Upon the loss of the leaving group, water attacks the molecule via nucleophilic reaction. Then it acted as a proton acceptor by abstracting one of the hydrogen atoms to produce the hemiacetal form of the molecule. After that, the carbonyl group was protonated and hence ejected from the molecule as alcohol. Lastly, the water molecule abstracts another proton to form the ketone. Okay, so they summed up all the products. So this solution is correct. Okay, so question number 6. What is the hybridization of the carbon atom in CH4? Okay, so to answer this question, we would need to write out the Lewis structure for CH4, which is methane. So first we need to calculate the total number of valence electrons in this molecule. So carbon has 4 valence electrons, hydrogen has 1, and we have 4 hydrogen atoms. So we multiply this by 4 to give us 8 valence electrons. So now if we drew out a skeletal structure with carbon as our central atom, we can draw the 4 bonds to hydrogen. And if we recall that each bond contains 2 bonding atoms, then you can see that we already have our 8 electrons in this structure. So this is the final Lewis structure of methane. So now we need to find out carbon's hybridization. So there are 2 ways that we can do so. So the first is by using the Vesper theory, which we can then use a Vesper theory chart that summarizes the hybridization and the molecular shape and electron geometry. So if we analyze the carbon, there are 0 lone pairs and 4 bonded atoms. So now, using a Vesper theory table, we can find out its hybridization. So when you have 0 lone pairs and 4 bonded atoms, you have an sp3 hybridization. So this is one method, which is using Vesper chart. But let's say we aren't given a Vesper chart like during a quiz or something. So we just need to find its hybridization. Another method we can do is by counting the number of charge clouds. So charge clouds are both the lone pairs plus any bonded atoms or bond pairs. So for example, when we have one charge cloud, or let's start from 2 charge clouds. Then our atom is sp hybridized. When we have 3 charge clouds, we have sp2 hybridization. And we have 4 charge clouds, like in our example, then it's sp3. and 5 charged clouds, sp3d, and we can have even 6 charged clouds, sp3d2. So you can see in the Vesper table as well, this is related to like total domains on the very first column. So 2 domains is sp, 3 sp2, 4 sp3, 5 sp3d, and 6 sp3d2. Okay, so that's another method that's pretty easy. And let's see what the junior tutor said. Hybridization is the concept of the fusion of atomic orbitals in order to form newly hybridized orbitals. These newly formed orbitals influence molecular geometry and bonding properties. Hybridization is also an expansion of the valence bond theory and helps explain the bonds formed, the length of bonds, and the bond energies. The hybrid orbitals used depends on how many electron groups are around the atom in a particular question. An electron group can either be a lone pair or a bonded atom. Okay, so they have their examples. sp is when you can have a triple bond and the carbon only has 2 bonded groups. sp2, there's a double bond and there's 3 charged clouds. sp3, all single bonds. Okay, so this solution is correct. Okay, so question number 7. What is the molecular geometry of carbon tetrafluoride? Okay, so to answer this question, we first need to draw out its Lewis structure. So in drawing the Lewis structure, we need to find the total number of valence electrons. So carbon has 4 valence electrons, and fluorine has 7. And since there are 4 fluorine atoms, we multiply this by 4. And when we add these values up, we get a total of 32 valence electrons. Okay, so now let's draw out our skeletal structure, with carbon being our central atom since it is able to form multiple bonds and because it is the least electronegative. And we can draw our 4 bonds to fluorine, like so. And now we'll fill up all of the lone pairs on our terminal atoms so that they have a complete octet. So now if I count out all the electrons in this structure, you can see that I already have my 32 electrons. So this is already the correct Lewis structure. So now when determining the molecular geometry, we need to analyze our central carbon atom. So we'll see that there are 0 lone pairs, and we have 4 bonded atoms. So if we use a Vesper theory table, we can find out its molecular geometry. Okay, so when we have 0 lone pairs and 4 bonded atoms, we have a tetrahedral molecular shape and electron geometry. We can also see that the carbon is sp3 hybridized, and that the bond angles between the groups are around 109.5 degrees. Okay, so now let's see what the junior tutor said. They have the total number of valence electrons for both, and it's equal to 32. And when they drew out its Lewis structure, they also got a tetrahedral molecular shape. Okay, so this solution is correct. Okay, so question number 8. Draw the Lewis structure of the sulfate ion SO4 2-. How many valence electrons are present? What is the electron group geometry and molecular geometry? What are the bond angles? And is it polar or nonpolar? Okay, so this is question 8. And we first need to find out the total number of valence electrons for SO4 2-. So this is part A. So sulfur has 6 valence electrons, and oxygen also has 6, and we have 4 oxygen atoms, so we multiply this by 4. And we also need to take into account the overall charge of the ion, which is -2. So we need to add an additional 2 electrons to our electron count, which gives us a total of 32 valence electrons. So this will help us in writing the Lewis structure. So we'll have sulfur as our central atom. And let's see what happens if we were to draw out the 4 single bonds to oxygen and filled in all of the lone pairs. So if we were to calculate the formal charges of all of the oxygens, when we have a single bonded oxygen, it has a formal charge of -1. And we want our overall charge of the ion to be -2. But if we were to bring a pair of electrons down on 2 of the oxygens to form a double bond, then the overall charge of our ion would be -2. Okay. So now our Lewis structure looks like this. Okay, so part B says what is the electron group geometry and what is the molecular geometry. So to analyze this, we'll look at our central sulfur atom, and we'll see that there are 0 lone pairs and 4 bonded atoms. And by using a Vesper theory table, we can find out both its electron group geometry, molecular geometry, and the bond angles. So we'll see that when you have 4 bonded atoms, 0 lone pairs, the electron geometry is tetrahedral. And for C, molecular geometry is also tetrahedral. And the bond angles are 109.5 degrees. So lastly is the molecule polar or nonpolar. So oxygen is more electronegative than the sulfur, but if we look at our molecule, the dipole moments would cancel each other out. So therefore, SO4 2- is a nonpolar molecule. Okay, so the junior tutor said there are 32 valence electrons, and they have the correct Lewis structure by completing the octet of the central sulfur. According to Vesper, it has a tetrahedral molecular shape and electron geometry. The individual dipole moments are cancelled, making the ion nonpolar. Okay, so this solution is correct. Okay, so question number 9, we need to write the formula of magnesium nitrate, lithium phosphate, barium cyanide, and ammonium sulfate. Okay, so let's start with magnesium nitrite. Magnesium is Mg2 plus when it is in its ionized form, and nitrite has the formula NO2 2-. So this is an example of a polyatomic ion, and since their charges would be neutralized when added together, they react at a 1-to-1 ratio. So therefore, the formula of magnesium nitrate would be MgNO2. Okay, so now let's look at lithium phosphate. Lithium is a group 1 metal, so its oxidation state is only +1. And phosphate is another polyatomic ion, and its formula is PO4 3-. So if we look at our two ions, we can see that 3 lithiums are needed to neutralize the 3- charge on the phosphate. So the formula of lithium phosphate would be lithium 3 and then PO4. Okay, so C, we have barium cyanide. So barium is a group 2 metal. So it has the charge of 2+, and cyanide has the formula Cn-. So we need two cyanides to react with the barium. So its final formula is barium Cn2. So this whole thing is in brackets since we need 2 of those ions. And now let's do our last example, which is ammonium sulfate. So both ammonium and sulfate are polyatomic ions. So ammonium's formula is NH4 plus, and sulfate is SO4 2 minus. So now we see that we need two positively charged ammoniums to neutralize the SO4 2 minus ion. So again, we're going to put ammonium in brackets to signify we need two of them. And then we just end it off with the sulfate. Okay, so let's see what the junior tutor said. Since the charge of its ions are constant, fixed charge metals only form just one type of ion. On the other hand, metals that have variable changes form ions with different charges as well. Following elements, a total of 15, are all of the fixed charge metals. Group 1 and 2A, Group 3A, 1B, and 2B. So elements aluminum, gallium, silver, zinc, and cadmium. So this is how to name fixed charge metals with polyatomic ion containing compounds. You write the name of the metal, and then the stem of the name is the polyatomic ion with the suffix -ide. How to name variable charged metals with polyatomic ion containing compounds, the name of the metal plus its charge in Roman numerals, and then the same thing for the second word. Okay, so we have magnesium nitrate, and they also got MgO2. Okay. Yep, so that's correct because the nitrate ion has only a -1 charge. I thought it had a 2- charge, but that is for NO3. So the junior tutor is correct in that sense. For lithium phosphate, let me fix my notes. Okay, like so. Lithium phosphate, we have lithium metal, which is +1. Phosphate is PO4 3-. Okay, so that's correct. Barium cyanide, BaCN2. And finally, ammonium sulfate, NH4 2SO4. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.